Okay, so we're going to be looking at a bit more inclined planes again. You might be sort of sensing this pattern that we're sort of going forwards and backwards within various topics. We're sort of touching on inclined planes, then frictions, and now we're sort of going back to inclined planes again. Part of the reason for that is that at least within the Year 13 textbook, it's kind of split two different sections where it's talking about friction and inclined planes, and then it's also talking about systems that are changing and inclined planes. So you have a little bit of overlap, unfortunately. So, the negative side of that is that maybe some of the content might be a bit repetitive, but the positive side is that you get a bit more practice, at least with this particular topic. So if some of the stuff I say sounds like you've heard it before, it might be the case, but I'll try and go at it from a slightly different angle in each case if I can. So we're going to be looking at a bit more stuff related to inclined planes, and the idea is this is going to lead to considering situations where you've got an object which is moving on an inclined plane. Because before we were just thinking about stuff that's sitting on an inclined plane and it's not moving, it's static. But what happens if, say, you've got a ball rolling down a hill, or a sledge sliding down a slide or something like this? So that's the kind of situation we'll eventually be moving up to. Okay, so then the first thing I want to talk about is actually relates to a question I was asked. So I think it's worth actually just explaining it for the benefit of everyone, because it's a good question. And the question is, when I've got a slope, okay, and let's say I'm going to put in a specific value. Let's say that's 20 degrees, okay. If I then consider the weight of an object on that slope, so let's say there's a box there and it's got a weight. Now what happens when I split that blue weight arrow, that force, what happens when I split that into its components? So you could split that into components specifically, in the usual sense, along the plane, so along the slope, and perpendicular to the slope. So these are my two components. Okay, that one's going down, that one's going across like that. And the question was, this angle here, between the original weight and the other component of it, this is 20 degrees again. Is that always going to be the case, that you have here an angle and this angle? And if so, why? So it is always the case. So if that was 50, then this is 50. If this was 90, well, if that was 90, it wouldn't be a realistic situation. If this was 89, then this would be 89. So why is that the case? And the reason it's the case, it basically just relates to a little bit of geometry, really. So let me just get out a different coloured pen. I'm going to draw some additional lines. I'm going to draw a horizontal line here. Oh, let me just try and put that in a slightly better position. I've got a horizontal line. Okay, and let's think about this angle here. Can we agree that this is 20 degrees? I'd hope so. Let me just rub out the actual answer we're aiming for. So this is a horizontal, and the slope, this yellow line, is also the same horizontal, parallel to this red line, and we've also got the slope. So that's definitely 20 degrees. And now consider, let me mark it in yellow, this is a right angle right here. Okay, between the red slope and that blue component of the weight, that's definitely a right angle by definition, because we said we're splitting it up into components which are parallel to the slope and perpendicular. So if that's a right angle, then that means that this angle here in green, so between the yellow and the blue lines, that's going to be 70 degrees, right? Okay, and then let me just rub out that little bit of working there. We've also got an additional right angle, it's here, between the solid blue line and the dashed yellow horizontal line. That's 90 degrees. So therefore, if that's 70, we just do 90 minus 70, and we end up back at 20 degrees again here. Okay? And the logic we've just done will work for, you know, any number of degrees. It doesn't have to be 20. So in general, we'll say when the slope is at an angle of theta degrees, then the component of the weight adjacent to the weight itself will also be theta degrees there. And you can always assume that. So whenever you see that here, you can mark the same angle there, and vice versa. Okay, cool. All right, that'll be quite a useful tool to use, and you don't have to, you know, work out all that geometry. Right, so let's go to some examples again. As I say, it is a little bit repetitive. You can always skip past this example if you want to, but if you find it helpful to just see an example work through again, then stick around and we'll just quickly go through this one. So we've got a block of mass 10 kilograms sliding down a smooth slope, 15 degrees. Let's draw it. 15 degrees. Here's my block. Draw a force diagram to show all the forces acting on the slope. Remember, it's smooth, so we're not talking about friction. So there will be no friction in this scenario. Okay. So let's see. We're going to have the weight. What's its mass? Its mass is 10g. Its mass is 10. So therefore its weight is 10 times g. What else have we got? You're going to have the normal reaction. And is that it? Is it that simple of a question? No, that's it. So reaction force. And that's it, done part A. B, calculate the magnitude of the normal reaction. Okay, so the way we're going to do this is by splitting up components. So we split up the component of the weight. 90 degrees there. What's this angle here? It's going to be 15 degrees. And then, therefore, this component is hypotenuse 10g times cos 15. This component is hypotenuse 10g times sine 15. Okay. Then equating the forces that are perpendicular to this plane, to the slope, we've got R going upwards, and that's equal to the 10g cos 15 in the opposite direction. Must be equal because it's not coming off the slope or going into the slope. So R is equal to 10g cos 15. Really is that simple. Right, so that's the magnitude of the normal reaction. Let's just quickly write that as a decimal. 10g cos 15 is equal to about 94.66 newtons. Okay, that's part B done. Part C, find the acceleration of the block. So we're going to have to resolve in the other direction. The resultant and this component here aren't doing anything in terms of moving the block up or down the slope. So we're focusing on this component here. That's 10g sine 15. So we're going to use F equals ma. And in this case, our force, that's the 10g sine 15, going horizontally, or along the plane, I should say. And that's equal to the mass, which is 10 times the acceleration. That implies that the acceleration must be equal to g sine 15. So that's 9.8 times sine 15. I type that into my calculator and I get 2.536, roughly speaking. Okay, I never really round these things, depends on the question. 2.536. And that's our answer. Done. Okay. So now, since we briefly looked at this thing about the angle of the weight component, I just want to introduce this concept of having a force which it's neither it's acting on the object, and it's neither going up the slope or perpendicular to the slope, much like the weight, and how we can split that into the relevant components. You'll see what I mean when I draw a diagram. So let's quickly draw one up. Slope. And let's make up an angle for the sake of illustration. Let's call it 20 degrees actually. So it's a 20-degree slope. Let's say I have an object, a ball. Okay. And you might sometimes be told, okay, there's a force acting on this ball, and they might say this force is acting at an angle of 50 degrees to the slope, or something like that. Let's go with 80 actually. So let's say 80 degrees. So if I draw that on here, what that means is, so I'm drawing the force a bit funny here, but the force is acting on this ball, and I said 80, didn't I? So it's saying, what it's saying is that the angle here is 80 degrees between the force and this slope. Okay, so this is an example of a question you might get, how it might phrase the information. It might say the force, this one, is at an angle of 80 degrees to the slope, and it means it looks like this. And now here is how you should split that up into components, okay, which you will probably have to do. So remember that when we split into components and we're talking about an inclined plane, we're splitting always. One axis is the direction of the slope and the other axis is the one perpendicular. Okay, and of course you can see that this, this arrow here, if I just move it for a moment, it's neither of those. It's not either of those two yellow lines, so we're going to have to split it up accordingly. Okay, the first thing you want to do is, I recommend, make sure that you draw or redraw, if you have to, the diagram so that the force head, so that is the arrowhead, it's not on the object but it's acting away from the object, because that lines up more realistically with how we should draw force diagrams. So if it looks like this, the arrow, I would suggest moving it so it's like that instead. Okay, I mean both versions are sort of accepted, I suppose, but I don't think I think it's confusing and it's unhelpful to mix them up in that way. Okay, so really we should have the force like this. But then where does the 80 degrees come into it now? We've got to be a bit careful with that. Where does the 80 degrees come into it? Well, if we just draw a horizontal appropriately, so let's say, let's draw a horizontal line here. Okay, can we think about what the angles are involved in this? Actually, take that back. I'm gonna draw the yellow line to be the perpendicular to the plane. That's probably more useful actually, because that's the angle we're really interested in, isn't it? Okay. So let's see if we can figure out what that angle would be. Well, here's what we can do. If you imagine, right, the original force was like this, that dashed red line, and we had the angle 80 degrees here. So whenever you want to do stuff with these sorts of angles, just add a few lines to make things easier for yourself, according to the 90-degree rules. So if that's 80 degrees there, what's this one? That must be 10 degrees. And then, because we've got here two lines crossing, right, the red lines and the yellow line, they cross each other. So therefore, by opposite angles, we know that this thing is 10 degrees. Okay, so that's what we really need to know. And now we can sort of split it into components. If I just rub down this yellow line a bit, that red force, I can now say, right, we're going to split it like this. and that angle there is 10 degrees. So whatever that force is, let's say it was capital F newtons, then this component here is going to be the hypotenuse times cos of 10, and this one here is going to be the hypotenuse F times sine of 10. Okay, and then we can, if we want to, we can sort of remove all this working just to point out that this is what we were originally going for. Okay, so just to summarize, what we did was we took a situation where we were told there's some mystery force acting on an object and it's acting at an angle of 80 degrees to the slope. Then with a bit of geometry, we figured out what the two components of that force is, where we picked two components such that they are, one of them is parallel to the slope and one of them is perpendicular to the slope, and that's what we have here. Okay, so it's all about drawing a big diagram, getting the geometry right, and just playing around with it a bit. Okay, cool. All right, let's look at another example. So how appropriate, it's got exactly this kind of question. So we've got an object and it's smooth slope, no friction, so we don't have to worry about that, and there's a force of magnitude 5g and it's acting at an angle of 60 degrees to the slope, and it's causing the particle to accelerate up the slope at 0.5 meters per second squared. Okay, so this object here, it's got the weight pulling it down in some sense, but then this force of 5g is strong enough to counteract that weight, and not only counteract it, actually cause it to move up the slope instead. Right, and we're going to show that the mass of the particle must be this. So the way we're going to do that is by drawing a nice diagram and resolving the forces. In fact, I'm going to try and get away with drawing it directly on the diagram. That might be a bit faster. No, wait, no, I'm not, because actually, as I said, this force, the arrowhead, it's not in a good position. I'm going to move that because I personally don't like that the arrowhead is on the object. It should be an arrow going out of the object. So let's redraw it so it's a bit more accurate. Plus then we've got a bigger diagram. Okay, so there's my slope. There's my 30 degrees. There's my object. And let's draw that mystery force on here. So now I'm just going to do that same trick again. Let's extend that arrow briefly, draw in the relevant angle, which was 60 degrees, and think about the perpendicular to the slope, which is that yellow line. What's the missing angle here? That's 30 degrees to add up to 90. And then by opposite angles, we've got here 30 degrees. Great. And then let's rub all this out because we don't need it anymore. And we can finish off splitting up that component of that 5g force. So if that's 5g, therefore we have that this bit is going to be 5g sine 30, and that bit there is 5g cos 30. Okay, great. What other forces are acting on it? We've also got the weight itself. Actually, this is why it's good that we've drawn a full diagram, because it'll get a bit messy if it's too small. If we've got the weight acting downwards here, okay, and that is, what is the weight? Have we been told? No, we don't know, do we? It's a mass of m, so therefore that will be mg. Our goal is still to find m. If we split that into components, let me make them blue just to try and distinguish this. We've got sort of two different components acting in two different places. This is a little bit messy, but let's see if we can do it. What's that angle here that I'm marking out going to be? What do you think? That's also 30 degrees, right? completely unrelated to that 30 degrees. It's just a coincidence, really, that these both end up being 30 degrees. That one's 30 because this one's 30. So now, what are these components? This blue component going that way, which you can hardly see, but I have drawn it on there. That blue component, let me try and draw it with a blue line there. That is going to be mg cos 30. And this other component over here, that one's mg sine 30. Okay, getting a bit messy. And we've also got one more force, which is the reaction. So the reaction force is going upwards. Let's just call it R for now. Okay, cool. All right, and so we've got basically most of the diagram on there then, don't we? We've got the reaction force, which is perpendicular, the mystery force 5G, which is split into its two components, and we've got the weight mg, which we've split into these two blue components here. Okay, now how are we going to show that the mass of the particle is this? Well, we've got this bit of information here about the acceleration. It's 0.5 meters per second squared. So if we know the direction of the acceleration, then we can just resolve forces in that direction, right? So which way is it accelerating? It's up the slope, so it's just accelerating in a line which is along that slope. So let's resolve in that direction, because then we can say that's equal to ma, mass times 0.5. Okay, so what are the forces acting in that direction? We're resolving in this upwards direction here. So that resultant force is irrelevant. So then what about the 5G? It's got two components. This component here is irrelevant because it's perpendicular to the slope. And we've got this one here, which is going upwards by 5G sine 30. So let's make a note of that one. We've got 5G sine 30 going up. And then for the weight, we've got this component here, which again is perpendicular, so it's not relevant. And then this component here, which is going down the slope, right? It's going down by mg sine 30. So let's take that one away. Minus mg sine 30. And that's going to be equal to what exactly? Well, remember, this whole thing, this is our resultant force, that's the F, along the slope. So that's going to be mass times the acceleration. And in this case, we're told the acceleration's a half. So let's just call that half m. Great. So then we can say, well, that implies that m must be equal to, and I'm just going to, I'm going to do two things at once. I'm going to combine these two terms, and I'm also going to multiply by 2. So then I just have m equals. So combining the terms, that's 5 minus m times g sine 30, and then doubling it, so we've got 2 on the outside. Ah, but wait, no, hang on, we can't use that strategy. No, that's a dead-end route. Reason being, we really want to find m, don't we? So we should collect together all the m terms. Right, so let's not do that, actually. That's a bad idea. That would assume it's too simple. So because we've got an m here, we need to get that m and this half m together. So let's do that instead. So I'm going to say a half m plus mg sine 30, that's equal to 5g sine 30. Okay. Right, at this stage, probably I think we should get rid of this sine 30 because it's actually a very easy value. We should know what it is. It's a half. Okay, sine 30 is equal to a half. So let's get rid of it because otherwise we're just going to be manipulating expressions that are more complicated than they need to be. So that's a half m plus a half mg equals 5 over 2g. And then in fact, let's multiply everything by 2. So half m becomes m, half mg becomes mg, and 5 over 2g becomes 5g. Okay, let's just make a bit of space. So now let's collect the m terms together. So we've got one lot of m plus g lots of m, factoring there, and that's equal to 5g. And then all we do is divide both sides by 1 plus g, so we get 5g all over 1 plus g, and that's it, we've got the answer. We have found the mass of the object. And it matches. Perfect. Cool. Just one thing to point out here, these two components, the component of the weight that's going in that direction, the blue one, and the component of the 5g, the yellow one, going in that direction. Just remember that, although whether you draw it that way or not, there's no reason to assume they're the same length. So we've sort of got a big triangle here, and then another triangle here, and although they're sort of back to back, there's no reason that they would line up in terms of having the same length for the side that goes along there. Okay, so just be careful to not draw it that way, because it might give the false sense that they are the same length. But the yellow line going along here and the blue line going along here, there's no reason that they would be the same length, you know, unless mg happened to be the same as 5g in this case. Cool. All right. So I had a slide here for the note on the placement of force arrows. This is a very short note, which is to just reiterate again that when you have an object, if you ever see in a diagram, this is my recommendation, if you ever see in a diagram them drawing a force like this, and they say the force acts on the object like that, I would personally just say, I'm going to reinterpret that and say the force looks like this, because that's a far more helpful way of visualizing forces, because the arrow really is indicating that the start of the arrow is where the object is, and then the force goes out from that. The reason why they sometimes might draw it like this is because this kind of looks more like a pushing force, whereas this is more of a pulling force. But, you know, in terms of how the universe really works, there's not really any distinction. A force is a force. A force moves, is a tendency for an object to move in a specific direction, a given magnitude and a given direction. And this arrow here has the same magnitude and direction as this arrow here. And I think it just overcomplicates things when you start having a mixture, if you see what I mean. If you start, you know, having forces labelled like this and like this, it all looks a bit weird, because you've got, you know, the arrow starts here and the head is down here. But in this case, the arrow starts here and the head is on the object. So I would prefer that you would just draw things so that, you know, it would look a bit more like that, except without all the bits and pieces falling off it. Hang on. So that would be, I'd say, a more reasonable way. And it means you can sort of picture it a little bit better, what's going on. Yeah, so that's what I'd recommend. That's my note on the placement of force arrows. Okay, right, one final example before I give you some questions. Let's see if we can get through this one quick. Particle 2 kilograms, it's on a smooth slope, no friction, force 4N, parallel to the slope. Beautiful, that makes the calculations more simple because it's parallel to the slope. And the slope is inclined at an angle alpha to the horizontal, where tan alpha equals 3/4. Okay, I think the key takeaway from this example is a note on how you're treating this tan alpha business, which some of you may be used to and some of you may not be. Let's see how that crops up. So this object has mass 2 kilograms. Let's draw the force. So that's 2g. Let's do the components. Yellow's not a good choice there. Let's do the components. The angle here, that's going to have to be alpha to match the angle of the slope. And then this component here is then clearly 2g cos alpha, the adjacent, and this one's 2g sine alpha, the opposite. We've got the reaction force then here, And in fact, because this mystery 4 newtons force is parallel to the slope, it has no component vertical to it. In that case, that reaction is just going to be the same as this blue component here, the 2g cos alpha. So let's actually just label that as well. It might not be relevant, but let's just label it on just in case. Okay, and then the question is, what's the acceleration? So we're going to resolve up the slope. We don't actually know if it's going up or down the slope. We'll find out. It depends on if we get a negative or positive answer. Let's say up the slope. What's the force going up the slope? We've got 4 newtons going up. And we've also got this 2g sine alpha going down. Okay, 2g sine alpha going down. And that's going to be equal to the mass times the acceleration. The mass is 2, and the acceleration is what we're interested in. So that implies, let's do some rearranging. Acceleration equals 2 minus g sine alpha. Is that right? Let me just double check. Yeah, that should be right. And now the question is, how are we going to get sine alpha if you've got tan alpha? And this is a technique that crops up in all sorts of places. Hopefully you're familiar with it, but let's just remind ourselves just in case. If you're ever given a trig function of an angle equal to a number, and you want to find the other ones, there's all sorts of techniques you can come up with. You can use trig identities, or in this case, when it's an easy fraction like this, I would just quickly draw up a triangle. So, not like that. If you have a triangle like this, let's now think, if I put the alpha somewhere, not at the right angle obviously, but one of the other two, and now think, right, if tan alpha is 3/4, what must the ratio be between the opposite and the adjacent? So remember, tan alpha is opposite over adjacent, therefore the 3 can represent the opposite, and the 4 can represent the adjacent. So the opposite is here, that's 3, the adjacent is here, that's 4. So that's me taking tan alpha equals 3/4 and applying it to a specific triangle. And then just use Pythagoras to find the missing side. And because it's 3 and 4, that's intentional, it's just a 3, 4, 5 triangle, isn't it? 3 squared plus 4 squared, square rooted is 5. So then you can easily get out your other ones, sine alpha and cos alpha, by just considering the relevant fractions. Sine alpha is opposite over hypotenuse, so that's 3 divided by 5. And cos alpha is adjacent over hypotenuse, so that's 4 over 5. And we're done. Okay, so if tan alpha is 3/4, you can try it on your calculator. Tan inverse of 3/4, then applying sine will give you 3/5. But really you don't need the calculator, you can get an exact value by doing this technique. So since sine alpha is 3/5, let's continue here now. We've got 2 minus g times 3/5. Really I should write that as 3/5 g. And let's work that out. So it's 2 minus 3/5, that's 0.6 times 9.8. And you get minus 3.88. Right. And then y minus, what's that telling us? So we have to be careful here and acknowledge what direction were we resolving in. I know we were resolving along the slope. We were resolving along the slope, but which direction? We were resolving upwards. So that means any answer we get will be relative to the idea that up the slope is a positive number. So if we get a negative answer, that must mean this is down the slope. So it's accelerating at minus 3.88 meters per second squared down the slope. Okay, so don't get caught out by that, because you might think, okay, I've got an object on the slope, there's a force pushing it up, obviously it's going to go up the slope. But no, not necessarily, right? What's actually happening here is you've got this object and it's 2 kilograms, it's going to go down the slope, and there's a force of 4 newtons pushing back, but it's not enough, it's not good enough, it's still going to go down the slope. So you can kind of imagine it as like, you know, you've got a boulder rolling down a hill. You're pushing at it, but you're not strong enough. It's still going down the hill. It's going slower because, you know, your pushing isn't doing nothing. You are slowing it down, but it's still going to go. And that's exactly what's happening here. This ball is accelerating 3.88 down the slope, and this puny 4 newtons is doing its best to slow it down, but it's still going to go down the hill. Okay, cool. All right, so let's have a go at some questions yourselves. Just got 3 questions for you to try. This is the first one. Just to start off with something involving exactly that tan trick that we just mentioned. So give this one a go. When you're ready, pause the video now. Okay, and let's look at the answer. Okay, next question. So, object on a slope, mystery force, acting completely vertically. You're going to have to divide that 6 newtons into components, presumably. So give that one a go. Pause the video now. Okay, and let's take a look at the answer. So in this one you did have friction, didn't you? But you didn't have to worry too much about the particulars of how friction's working. It just said there was a constant force. And you got 15 newtons for that one. Hopefully. Okay, and let's look at the final question. So getting a little bit tougher here. You've got an object, 2 different forces acting on it. 2 different mystery forces. In addition to that, of course, you'll have the weight and the reaction force. So get the weight and reaction force on there, and then see if you can answer the question by resolving along the slope. Give that a go. Pause the video now. Okay, and your answer, there it is, mass of 1.08 kilograms.